All right, welcome to our video on double displacement reactions. By the end of this video, you should be able to predict the products for all the different types of double displacement reactions. And as you can probably remember from grade 10, the general structure of a double displacement reaction looks something like this, right? You've got two compounds on your reactant side and two new compounds on your product side. What ends up happening is that you have two of these elements that are switching places so that there are two brand new products on your product's side. And although this is the general structure of a double displacement reaction, there are a few different types of the double displacement reaction themselves. So the first of which is a reaction that forms a precipitate, a solid. So in order for it to fall under this category, you should have two reactants, both that are aqueous. When they're reacting together, should form one aqueous product as well as a solid product. That one solid product is the precipitate. Okay, so let's take a look at what this might look like. So here's our first example. I've got AgNO3, silver nitrate, plus sodium chloride. They're both aqueous on the reactant side. And what you want to do first is try and predict what the compounds will be, right? So remember, just as we saw in our general structure, you're switching one of the two. I like to think that we're switching the metals, but if you like to think that we're switching the nonmetals, that's fine too. So now instead of Ag being linked to nitrate on your product side, it's going to be AgCl and NaNO3, right? So Ag, remember that when we're trying to predict our products, we have to use our crisscrossing. So Ag has a charge of +1, Cl has a charge of -1. And when you crisscross these together, I will get AgCl. Plus, now I have Na and NO3. Again, same situation here. Na plus 1, NO3 has a charge of -1. When I crisscross, I get NaNO3. So I've got two different products here. Now I have to figure out which one of these is my precipitate. So I have to, for these double displacement reactions, always write down the state of it, right? In order for us to do that, we have to look at a chart. And now this is called our solubility chart. And there is a very unique way we have to look at these in order to determine the state of our compound. Let's start with NaNO3. Okay, so whenever you're looking at a compound, so I'm going to write my compound here just so that we can keep that in mind as we are looking to see its state. You have to first start with the anion. And the anion in this case is NO3. So let me try and find which category NO3 falls under. So if you see here, I've got NO3 right here. And NO3, so I have to follow that line to try and determine where my metal falls in that category. But luckily for us, most things that are linked to the nitrate, most cations that are bonded to our NO3 are going to be soluble. And whenever you see soluble, that gives you the state of aqueous, AQ. Remember what aqueous means, right? Soluble in water, or dissolved in water. So NaNO3 has the state of aqueous. Now, let's take a look at Cl, or AgCl. As I kind of gave it away, you have to start with the anion, and the anion in this case is Cl. So let's try and see where Cl falls into, which category it falls into. So I've got chloride right here, so Cl. And now here's where I have two different options, right? I have two different paths that Cl can take. So there are certain cations that are listed here that have a certain outcome, and all of the others have another outcome. So let's see, I've got the cation that it's linked to right here is Ag, and Ag is in one of these listed up here. So Ag has a low solubility, and whenever you see low solubility, that the state that we would write is S. And S as in solid. So that means that it will not dissolve. It would rather be solid. And this is our precipitate. And if we were to do this reaction in front of us, we would actually see the precipitate being formed, right? Any precipitate that's formed in a reaction is visible to us when we do that reaction in front of ourselves. Okay, so this is this reaction. It is already balanced. Say it wasn't, I would have to balance it, but for now I'm good. And I know that this reaction occurs because it forms a precipitate. Okay, let's take a look at another example. So in this case, I've got calcium chloride plus potassium nitrate. I'm going to do exactly what I did in that first time. I am going to figure out what my products are going to be. I'm going to have K and Cl that are going to be bonded together, and Ca and NO3 going to be bonded together. Just to be consistent with what I did earlier, maybe I'll just draw my line to show which ones are switching. So I like to think that the metals are switching, right? Calcium and potassium are going to switch places. So now the potassium and the chloride are going to be together. So K has a charge of +1, Cl has a charge of -1. When I crisscross these, I'm going to get KCl plus I have Ca going to be linked with the NO3. So Ca has a charge of +2 because it's in group 2. NO3, polyatomic ion nitrate, has a charge of -1. When I crisscross these, I'm going to get CaNO3 2. Okay, now I have to figure out the states of these, right? If a precipitate is produced, then that reaction occurs. If not, it doesn't. So in order for us to figure that out, we have to use our solubility chart again. So let's start with KCl. KCl. So again, I'm going to try and figure out where my anion, my Cl, falls, which category it falls into. So right now it falls here, so Cl. And then I have to try and find the anion. So K, which category does K fall into? So it's not one of these metals that are listed up here, but rather it falls into all others. And all others are soluble. So because it's soluble, I know that my state is aqueous. It is able to dissolve. Now let's try CaNO3 2. Calcium nitrate. Again, starting with the anion, I'm looking at nitrate. And then because there are no two categories, it's just the one, most things that are bonded to nitrate are going to be soluble. So I know that it is soluble. AQ. So now there's no precipitate formed at the end of this reaction. And because that's the case, because there isn't a precipitate formed, and you will see scenarios like this, we don't write the products. In fact, we consider this reaction to not occur. So I know we had to do all of this hard work of trying to figure out which compounds are bonded with the other, but we have to do that in order to figure out what our products could be and check to see if they, what the state would be on the solubility chart. So I would write no reaction. So whenever a reaction, whenever you're presented with a double displacement reaction, figure out theoretically what the products would be and check to see if a precipitate is formed or not. If a precipitate is not formed, you would write no reaction. So you can see how you have to get really, really familiar with this chart and have it ready and available when you're doing your assessment so that you can check pretty quickly the state of all of these different compounds. Okay, so having done the first reaction, let's take a look at our second type of double displacement reaction. In the second type, you've got an acid, any acid, reacting with any compound that contains a carbonate. And we'll see what happens there. So you've got one acid reacting with a compound that contains a carbonate. So here's my example, HCl plus MgCO3. My acid is hydrochloric acid, HCl, and this compound contains a carbonate. Now, there's a very specific set of products that are formed here, but let's try and understand why. So we know that this is a double displacement reaction. So let's figure out or predict what our products are going to be. So I know that my hydrogen and my magnesium are going to switch places. So it's going to be magnesium and chlorine bonded together. Magnesium has a charge of +2, Cl has a charge of -1. When I crisscross, I'm going to get MgCl2. All right, that's one of my products. The other one, I've got H and CO3, hydrogen and carbonate. This is carbonic acid, which is H2CO3. Now, this is what we would expect as our products for this reaction. However, we have to take into account about what happens to this carbonic acid. And this is why this is a unique set of this is a very specific type of double displacement reaction, is because of what happens to this. This carbonic acid actually spontaneously or instantaneously becomes or breaks down into H2O liquid plus carbon dioxide gas. So because this happens when we are predicting our products, MgCl2, we would write our ionic compound, right? And then instead of writing H2CO3, we go straight into writing H2O plus CO2, right? And just to confirm the state of MgCl2, I can go back to my solubility chart, right? So Cl is right here, Mg falls into all others, it is soluble, so I'm going to write it as AQ, right? So my entire reaction or equation is this, right? I just have to make sure that this is balanced, and in order for me to do that, I think I can do that by just putting a 2 in front of my HCl. So that gives me 2 H's on the left side and 2 Cl's on the right side. Everything else is balanced. So see how the only thing that we did here is we recognize that carbonic acid, when it's produced, instantaneously becomes H2O liquid and CO2 gas. So we just go directly into writing this products. And when you're actually doing this reaction, you will see gas bubbles form. You will see the carbon dioxide escaping the liquid that you are reacting. So that's an indication, if you're seeing a reaction, that this reaction is taking place. The fact that the carbon dioxide is formed is that indication for you. Okay, so that is my second type of double displacement reaction. Now we're going to go into a third category. This is probably something that you've seen before, and these are reactions that form water, or neutralization reactions. And as you can remember from grade 10, hopefully, neutralization reactions usually occur when you have an acid and a base reacting together to form an ionic salt and water. So let's take a look at this example. I've got HNO3 plus NaOH. So in this case, what ends up happening is, again, this is still a double displacement reaction. Let's take a look at what two things are going to be switching places. So hydrogen and sodium are going to be switching places. So one of the things that's going to be produced are NaNO3, right? And Na has a charge of +1. NO3 has a charge of -1, crisscross it, I get NaNO3 plus, I've got H and OH. And remember from our single displacement video, HOH is the same as writing water, right? H2O liquid. So it forms H2O liquid and NaNO3. Remember from our solubility chart, all nitrate or most nitrates are soluble. So I'm going to put an aqueous there. So that is my neutralization reaction. Just quickly making sure that things are balanced. I've got 2 H's on the left side, 2 H's on the right side. O, 1 O there, NO3 stays together. That's good, that is balanced. Let's try a second example here. So if you want to pause the video and try it yourself, feel free to do that. But in this case, I've got HBr, so my acid, and calcium hydroxide, CaOH2, as my base. Like I mentioned, my calcium and my hydrogen are going to switch places. So I'm going to have CaBr. So calcium has a charge of +2, Br has a charge of -1. When I crisscross these, I'm going to get CaBr2 plus, I've got hydrogen and hydroxide, HOH, which is H2O liquid. Now CaBr2, I'm fairly certain that that is soluble, but let's just make sure using our solubility chart. Br falls right here. There is the category of all others, right? Ca falls into a category of all others, which means that it is soluble, which is aqueous, right? And those are the 3 different types of double displacement reactions. The only thing that's a little bit extra, just to summarize, so in our first type of reaction, if you ever get 2 products that are both aqueous, so in a situation like this, you would consider it as no reaction. In our second example, if you see carbonic acid produced, it breaks down into H2O liquid and CO2 gas, so we write it as 3 different products. Notice how even in this situation, you don't have just aqueous products, right? You've got a gas and a liquid. So this is still considered a reaction that occurs. And lastly, when you've got an acid and a base reacting together, you make an ionic compound and water, which is a liquid. Again, not 2 aqueous products. You've got H2O liquid and your ionic compound. So hopefully you understand everything about double displacement reactions. Take a look at the practice and then let us know if you have any questions.